So 3.4b today. And we're just going to jump right into a problem. So, of course, for a circle, area equals pi r squared. So for part A, I'm going to ask what is the average rate of change of the area with respect to the radius on the interval 2, 4. So we got area equals pi r squared. And the question is, what is the average rate of change of the area with respect to the radius on the interval 2, 4? Okay, so the new thing today is this, with respect to the radius. So far, all of our rates have been with respect to time. So we've said miles per hour or feet per second. So this is different. There's no time in this question. There's just the radius and the area. And so because of that, when we find the average rate of change, it's going to be radius on the bottom. And so the rate is going to be something per inch rather than something per second. And the way we say that that's going to happen is it's with respect to the radius. Okay, so let's figure out, this is a range of values, right? And these are r's. So this is r equals 2 inches. And that's r equals 4 inches. So we're going to figure out the area of a circle that has a 2-inch radius. So that is pi times 2 squared. So it's 4 pi. And then we're going to figure out the area of a circle that has 4 for a radius. So that's pi times 4 squared. So that's 16 pi. So the average rate of change is the area of a 4-inch circle minus the area of a 2-inch circle divided by the 4 inches minus the 2 inches. So it's still the same average rate of change formula. It's not a new formula. The only thing that's a little bit weird is there's not time on the bottom here. There's inches on the bottom. Okay, so we figured those out. That is 16 pi minus 4 pi. Got to pass from her or something. I don't know why. You got to be here on time, so yeah. Okay, so you got to take 16 pi minus 4 pi, and that comes out to 12 pi. And then if you take 12 pi divided by 2, that comes out to 6 pi. Okay, so what's going on here is the area used to be only 4 pi, and now the area is 16 pi. And so that means the extra area is 12 pi. So there's 12 pi extra square inches of area. So if there's 12 pi extra square inches of area. Used to be a radius of 2, now it's a radius of 4. So the picture is, here's the old circle, here's the new circle. There's an extra 12 pi of area out there, right? And that happened over 2 inches of extra radius. So on average, we got an extra 6 pi square inches for every inch. So let me say that again. There's an extra 12 pi of area out there, right? And that happened over 2 inches. So we got an extra 6 pi per inch. Now it wasn't 6 pi per inch, right? Because the first inch gave less extra area than the second inch. So that's why this is an average. On average, we got an extra 6 pi square inches per inch. Okay, and then it's kind of tempting maybe to cross out the 2 and the inch, but that doesn't really make sense. We want to know how many square inches per inch happened. Okay, and then for B, the question is, what is the instantaneous rate? With respect to the area. At R equals, let's see, I did R equals 2. Okay, so we already noticed that the rate is changing, right? 1 extra inch here gives a different amount of extra area than 1 extra inch here. So this is an average rate. So that means that the instantaneous rate is going to be reflective of what's happening right at, I don't want to say a moment because there's no time, but right at a particular picture. Okay, so the way you find the instantaneous rate is you take the derivative. So we've got our formula for area, and that's pi r squared. And we're going to take the derivative. Now usually we put a ddx here because we're taking the derivative and there's an x in the formula. And then if you want the derivative regarding time, you take d dt. But this time it's with respect to the radius. So we're going to do d dr. Okay, so we're taking the derivative with respect to the radius because we're comparing per inch on the bottom. So that's why it's d dr. Okay, when you take the derivative of a, you get a prime. And then when you take the derivative of pi r squared, well, the pi is a constant, so it's just hanging out. And then the derivative of r squared is 2r. So the area derivative is 2 pi r. So then if you want to know the instantaneous rate when r is 2, you just plug a 2 into that. So the area prime evaluated at 2 is 2 pi times 2. So that's 4 pi. Okay, so this is a little bit of a tricky question, but what would the label on 4 pi be? Yes? It's square inches per inch. Because the average rate was square inches per inch, and the instantaneous rate always has the same label as the average rate, so this is square inches per inch. Okay, so it's a little bit tricky to talk about what this means, but as the circle gets bigger, the rate keeps changing. Because when you have a large circle, an extra inch gives you a lot of area, whereas when you have a small circle, an extra inch just gives you a little bit of extra area. So what this means is, as the circle passes the 2-inch mark, right at the moment when it's 2 inches, the rate is 4 pi square inches per inch. So it's like if you drop a pebble in a pond, the circle keeps getting bigger. So the rate keeps changing, the rate of change of the area, and that's the moment. Again, moment is not a great word because it's not time, but right when this radius is 2 inches, it's going to be that rate of change. Okay, so that's hard to talk about because we're not used to rates of change with respect to things besides time. We're good at with respect to time, but this is a little bit different. It's with respect to other stuff. Okay, then example 2 is a little bit of a business example. So we're going to have a formula C of x that equals x cubed minus 6x squared plus 15x plus 24. And this is going to be the cost function. And what we're producing is radiators. So this is a C of x stands for cost. Yes? Oh, thank you. You can do it. All right. So C of x stands for cost, and x is how many radiators we're going to make. So for example, if we put 5 into here, this function will tell me how much it's going to cost me to make 5 radiators. Okay. So for part A, the question is, what is the average cost of producing 8 radiators? Okay, so this is not the average rate of change. There's no rate of change after this average. So this is a little bit different than average rate of change. So what we're going to do is we're going to plug 8 into the cost function. And that's going to tell us how much it costs to make 8 radiators. All right, so I need a calculator for that. So that's 8 cubed minus 6 times 8 squared plus 15 times 8 plus 24. So that's 272. Okay, so what that means is this company is making radiators, and they decide to make 8 of them, and it costs them $272 to make them, all of them, all 8. Okay, so then the average cost is that cost divided by 8. Right, so average cost is how much it costs to make all of them divided by how many you made. So again, it's not an average rate of change. I'm not subtracting here. So that's $34 per radiator. So just to point out again, this is not average rate of change. There's no subtraction on top and bottom here. If it's an average rate of change, it's 2 things subtracted divided by 2 things subtracted. This is just a plain old average. So it's just 2 things divided. A total divided by how many? Okay, so that's $34 per radiator. So what that means is they made 8 radiators, and on average, it cost them $34 per radiator to make them. It could be that for some reason it's more expensive to make the second radiator as opposed to the 8th one. Yeah, Brandon, you got a question?
Is there a difference in doing all that work and putting quantity into the function?
Yeah, because it might cost a different amount to make the first one as opposed to the 8th one. They don't necessarily all cost the same amount to make. That was a really good question that Brandon just asked. He was thinking, hey, wouldn't it make sense that they would all cost $34 to make? That was a reasonable thought on his part. And in which case, if you plugged a 1 into here, you should get 34, because that would be the cost of one radiator. Okay? So that was a reasonable thought, but the only thing that was slightly off is it might cost more to make the first radiator as opposed to the 7th or the 8th. Good. And that's the way business generally goes. The first one's pretty expensive because you're trying to figure out how to do it, so it might take you longer. That's just one reason why the first one might take more money, because you have to pay people more wages to make it. Okay, so $34 per radiator is the average for 8. And then for part B, the question is, find the cost to produce the 9th radiator. Okay, so in order to figure out how much it costs to produce the 9th radiator, I'm going to figure out how much it costs to make all 9, and then subtract how much it costs to make 8. And that'll tell me how much it costs to make just number 9. So the cost to produce 9 is C of 9, and the cost to produce 8 is C of 8. Okay, so now I got to plug 9 into my function. So that's $402 for 9 of them. And then it was $272 for 8 of them. So for some reason, this number 9 radiator is really expensive. So I'm not sure what's going on with this company, but maybe you have an employee that can make 8 radiators in a day. And then you have to hire somebody new if you're going to make 9. So maybe that's why the 9th one is costing so much. Could be that you need a second employee for 9, as opposed to you only needed 1 employee for 8. That's just one possible scenario. So as you can see, it's costing different amounts to make different radiators. The first 8 were only costing $34 per radiator, but number 9 is $130. Okay, so now that last one could be thought of as a rate of change. So if I write it like this, that wouldn't change my calculation, right? So this is exactly the same thing as I just did. I'm just dividing by 9 minus 8 to point out that, so this would come out to $130. So what I'm pointing out is that the cost to produce radiator number 9 is the average rate of change on the interval 8, 9. So let me say that again. The cost to produce radiator number 9 is the average rate of change on the interval 8, 9. It's the same idea. Okay, so if we graphed this, x and cost, then we've got our graph, which I'm not sure what it looks like, but I do know that from 8 to 9, the slope of the secant line, aka the average rate of change, is $130. And that's the exact cost for finding the radiator number 9, for making radiator number 9. So this is a different scenario. In this situation, the slope of this line is exactly what we want. It is the exact cost to produce radiator number 9. Okay, but the derivative is so easy and so famous that sometimes we calculate the derivative. Okay, so this is part C. And what we're going to do is we're going to find the marginal cost at x equals 9. So I need to tell you what marginal cost is. What marginal cost is it's the derivative of cost. So when it says find the marginal cost at x equals 9, all they're saying is take the derivative of the cost function and plug 9 in. Okay, so let's write the derivative of the cost function. And that would be 3x squared, so the x cubed. Then the 6 is hanging out, right? And the 2 comes out front. So it would end up being 12. And then x to the first power, because 2 minus 1 is 1. Then the 15 is hanging out, and the derivative of x is 1. So it's 15 times 1, which is 15. And then the derivative of 24 is 0. Okay, so there's the derivative of cost. And now we just need to find the derivative at 9. So C prime at 9. So that's 3 times 9 squared minus 12 times 9 plus 15. And that comes out to 150. Okay, so this is a slope on this graph, right? And down here we have radiators. And up here we have dollars. So the slope would be dollars per radiator. And then pictorially, what we just found right here is we found the slope of this line, right? The slope of the tangent line at 9. Okay, now in this context, it doesn't make sense to connect the points, because we're not going to make 8.5 radiators. We're either going to make 8 or we're going to make 9. So because of that, the derivative doesn't really make complete sense, because to have a derivative, you have to have infinitely close, so you have to have a connected graph. But the derivative is so easy that sometimes we use the slope of this line to approximate the slope of that line. The slope of this line was our cost for radiator number 9, right? So sometimes we use this to approximate the cost for radiator number 9. Okay, so sometimes this is used to approximate the cost of radiator number 9. And that's kind of strange, because up until now, we've been using the average rate of change. Sorry, it's over here. We've been using the average rate of change to approximate the derivative, right? But now this is backwards. Now the derivative is approximating the average rate of change. And the reason it's that way in this problem is it doesn't make sense to connect. You can't make 8.5 radiators. So it's a different kind of a context. Okay, so marginal cost is the derivative of cost. So what do you think marginal revenue is? No, that would be marginal profit. So what do you think marginal revenue is? It's the derivative of revenue. Okay, so marginal cost is the derivative of cost, and marginal revenue is the derivative of revenue. Now, Josh, you did have something good to say in there, so I didn't want to just totally shoot you down, but let me get this down. So a marginal revenue is the derivative of revenue. So in business terms, the word marginal basically means derivative. Okay, so if we're going to find the derivative, if we're going to find the marginal cost, you just take the derivative, plug in the cost. If you're going to find the marginal revenue, you're going to take the derivative and plug in revenue. But what Josh was trying to get at is what this means, not how to do it, but what it means. And revenue is how much money you take in, right? So the marginal revenue is, if I make radiator number 9, I'm going to be able to sell it for this much. It's my extra revenue that I can get for radiator number 9. Or it's going to be the approximation, right? Because the actual revenue would be that, R of 9 minus R of 8. Okay, so the meaning of this then is it's how much extra revenue you can get, how much extra money you can take in if you make radiator number 9. Okay, then you mentioned profit. Profit comes in when it's revenue minus cost, right? So how much you take in minus how much you spent. And then that's what you have left over as your profit. So that comes into play as well. And there is something called marginal profit, which is the extra profit you get if you're going to make another radiator. And you would only want to make it if your marginal profit was positive. But if your marginal profit was negative, if you were going to lose money, then you wouldn't want to make radiator number 9. So that all connects to what you said. That's good. Okay, is everybody okay? You sure? I think that's all I have to say. I need to double check though. Yeah, that's it. So thanks for paying attention.